In this chapter on mechanics, we're going to look at something called projectiles, which is basically an application of kinematics and SUVAT that we've looked at already. Now, here I've got a little simulator set up to look at some projectiles, so some things being fired from this cannon. And I can change what speed I fire the cannonball at, and I can change what angle I fire it at. Okay, so let's fire it at 16 meters per second at an angle of 50 degrees to the horizontal. If we do that, we will see what happens. Okay, so it follows this nice parabola shape like this. Okay, now what I want you to actually look carefully at is what happens to the velocity as it follows this path. And I'm going to show you the two vectors for velocity. So we're going to look at the horizontal velocity and the vertical velocity. Okay, I'll show you again. So let's look at the horizontal velocity first. So horizontally, this green one that's just horizontal, notice that it stays the same throughout the whole journey. So the x component, or the horizontal component of the velocity, is exactly the same throughout the whole journey. Doesn't change. The reason for that is because there's no forces acting horizontally. So there's not actually any forces acting on this cannonball horizontally if we model it as being in a vacuum. Okay. If I turn air resistance on, then there would be. And you can see this green arrow is getting smaller and smaller and smaller, and therefore it goes less far. Okay. But in mechanics, we tend to do it without air resistance. Okay, which makes things a lot simpler. And it means that there's no force on the cannonball horizontally, so the velocity stays the same throughout. Now, hopefully you've been also looking at the vertical component. So when I first launch it, it has a vertical speed upwards. Once it gets to the top, its vertical speed is 0. That's something that we've used quite a lot when we did SUVAT earlier on. When it gets to the top of this arc, its velocity is 0 vertically. Now on the way back down, it's getting faster and faster and faster towards the ground. So it starts off with a positive vertical velocity, then it's 0, and then it's negative. And the reason for that is there is a force acting vertically, and that's obviously gravity. So it's accelerating at minus 9.8 meters per second squared. Now, the next thing we're going to do is going to try and calculate some things from this. So we know that the angle is 50, we know that the speed is 16. I'm just going to draw this as a simple diagram. So my diagram might look something like this. I'm firing it at a speed of, what do we fire at? 16 meters per second, an angle of 50 degrees. Okay. Now, what we're going to do when we analyze this is we're just going to resolve the velocity into a vertical component and a horizontal component, just like we did with forces. So the vertical component is going to be 16 sine 50 meters per second. The horizontal component is going to be 16 cos 50 meters per second. So just like we do with forces, we can actually resolve the velocity. Now I'm going to try and find out some things. The first thing I'm going to find out is what is the maximum height that it reaches. So to find the maximum height, I really want to be thinking about what's happening vertically. So I'm just going to look at the vertical forces, the vertical velocities. And we're going to treat it just like a SUVAT problem. So the initial velocity vertically is 16 sine 50. The final velocity, when it reaches the top, so the maximum height, is 0, just like we've done with SUVAT before. The acceleration is negative 9.8 because it slows down as it goes up. And then I want to find out what is the displacement. So I can use v squared equals u squared plus 2as. So if I calculate that, I've got 0 equals u squared. So it's going to be 16 sine 50 squared plus 2 times minus 9.8 times s. And then we can solve this to find out what s is. Okay, so if I do that, I get 7.66 meters. Let's check it on this simulator. So I fired it. It follows this path here, and I can use this to tell me what its height was. There we go, 7.66 meters. I can see that there. So another thing that we can work out is the time of flight. Now what this means is how long does the whole journey take? So in this case, it's how long does this whole journey take from here all the way back down to the ground. Okay, and we can calculate that in seconds. One way we could work it out is find how long does it take to get to the top, and then we could times it by 2, because this is a symmetrical path. So let's do it that way. So let's find the time to the top. So again, we're thinking vertically. U is still 16 sine 50. V is 0 at the top. We want to find t, and we also know that a is minus 9.8. So we can use v equals u plus at. And I can then solve that to find what t is. So we have 16 sine 50 divided by 9.8. So that's 1.25 seconds. So that's how long it takes to get to the top. So the total time is therefore 2.5 seconds. So we can double it. Let's check. So the time down here, 2.5 seconds. And obviously the time to the top is half that, 1.25. Now, we can only do this when it's symmetrical. Sometimes the path might not be symmetrical. For instance, if I did something like this, and now the path would no longer be symmetrical, it would have like a longer, if I zoom out a little bit, it has like a longer tail on the second half. So you wouldn't be able to find the time to here and double it. If you doubled the time, that would take you to about here, when it's back at the same height that it started at. So we need another strategy for doing this, really. So what we're going to do instead is we're going to consider when is the displacement equal to 0. And when I say the displacement, I mean the vertical displacement. Because at the start, it's got vertical displacement 0. And at the top, it's got vertical displacement 7.66 meters. And then when we get back down to the floor, it's got a displacement 0 again. So we can do it that way. And we used this method when we did SUVAT before, when we were just doing it in the year 1 content. So, or we can say that u is 16 sine 50. And then we can't use v in this case. We want to find out what t is. A is minus 9.8, but we also know the displacement is 0 vertically. And we can then use s equals ut plus half at squared. And we will then get 2 answers out if we do that for t. We'll either get t equals 2.5, just like we did for the last one, or we will get t equals 0, because the other moment in time when its displacement is 0 vertically is at the start, when t is 0. So we can do it that way. Okay. The last thing that we can work out is the range. Okay. Now the range, this is how far it goes to the right. So basically, how far along the ground does it go? So to find the range, we want to think horizontally now. So this time u, instead of being 16 sine 50, because we're thinking horizontally, it's going to be 16 cos 50. Okay, so it's cosine rather than sine, because we're looking at the adjacent to the angle. For the horizontal range, we want to find s. So I'm just going to say that s is s. We don't really know what the final, well actually we do know what the final velocity is to the right. It's still going to be 16 cos 50, but that's not really going to help us solve this problem. The acceleration to the right is 0. Remember how we talked about there's no forces left and right. So what other information have we got? Well, we've got t. We know the time of flight is 2.5 seconds. Okay, so finding the range relies on you knowing the time of flight to help you. So now we can look horizontally and we can use s equals ut plus half at squared, which for us is going to be s equals 16 cos 50 times 2.5 and then plus 0, because the acceleration is 0 horizontally. So we're essentially just using s equals ut. So 16 cos 50 times 2.5, so 25.7 meters. So when it reaches this point here, yes, 25.7 meters is the range. Okay, so I'm going to give you one to do for practice, and then we're going to go through the solutions. We want to find the same three things. We want to find the maximum height that it gets to, the time of flight, and the range, and then we're going to check it using this simulation. So let's go for 70 degrees and 30 meters per second. We'll fire it as fast as it can. So 70 degrees and 30 meters per second. Oops. Okay, so we want to find how high does it go, how long does the whole trip take, and how far horizontally does it go. So you might want to pause the video and have a go at calculating that yourself. So the first thing I'm going to do is I'm going to split the velocity up into its two components. So I've got 30 sine 70 and I've got 30 cos 70. So to find the maximum height, I'm looking vertically. U is going to be 30 sine 70. The final velocity, because we're looking at the maximum height as the top of this arc, so at the top V is 0. A is minus 9.8, because gravity acts vertically and pulls it down. It's trying to slow it down, so it's negative. And we want to find S. So we've got 30 sine 70 squared divided by 2 divided by 9.8. Let's get S is 40.5 meters. That should be the maximum height. Now let's find the time of flight. So this is for the height. So for the time of flight, we can still think vertically. We can do U equals 30 sine 70. I think I'm going to do it using the fact that displacement equals 0 this time. So again, like we talked about, you could find how long does it take to get to the top and then double it because it's symmetrical. But I do prefer to use the fact that displacement equals 0 at the bottom, just because it's a bit more robust when we come on to paths that aren't exactly symmetrical. A is minus 9.8, and we want to find T. Okay, so we've got 0 equals 30 sine 70 T plus half A, so that's going to be minus 4.9 T squared. And then I can solve this to find my values of T. So I get 5.75 or 0, because the 2 times when its displacement is 0 is after 5.75 seconds or at the start. And the last one, the range. So the range, I need to think about horizontal. So this time U is going to be 30 cos 70 instead. A is 0 horizontally because there's no gravity horizontally, it only acts vertically, and we're not looking at air resistance. We want to find the distance, and we know that the time it takes is 5.75 seconds. So we can use S equals UT plus half AT squared, which because A is 0, basically becomes S equals UT. So you've got 30 cos 70 times 5.75. So about 59 meters. Okay, let's check these results and see if they're right. So we reckon our range is 59 meters. Let's move this target to 59 and see if we're right. Okay. Okay, so we are right for our range. We can see that the range is 59 meters, or rounds to 59 meters. We can also see the time of flight here is 5.75. The maximum height, we predicted the maximum height was 40.5 meters. There it is, 40.5 meters. Excellent, so that's all worked nicely. Okay, so we talked a little bit about when we can use that doubling kind of shortcut. And I said about how I preferred not to use it. I would rather use displacement equals 0. So let's look at one where we can't use that. So let's change these values back a bit. Let's change the speed to 20 and the angle to 50. Okay. And this time I'm going to start it on a platform of 10 meters. Okay. So if it starts on a platform of 10 meters, this is what it's going to follow, this kind of arc. Okay. So if we want to think about the time of flight now, well, this point here is s equals 0 vertically. This point up here is whatever we calculate the maximum height to be, which we can do in exactly the same way. Maybe we'll do that first. Let's find the maximum height. So u, if we split this up, the vertical component is going to be, I can't remember what the speed was now, 20. So we have 20 meters per second. So this is going to be 20 sine 50. V is 0 up at the top. A is minus 9.8. We want to find S. We get about 11.97, so 12 meters. Now that distance is from where it started. So what I found there is that, which is 12 meters. So its height off the ground is then going to be plus an extra 10. So that's 22 meters above the ground. If you're in an exam or just doing a textbook question, sometimes it might ask you for the height above the ground. Sometimes it might ask you for the height above where it started. So just be wary of that. Now to find the time of flight, this point is displacement 0. This point up here is displacement 22. This point here is again s equals 0. So this point down here is s equals negative 10. And that's what we can use to help find the time of flight. So if we look vertically, u is still 20 sine 50. We want to find t. A is minus 9.8. And the displacement we can use as minus 10. And then we can use s equals ut plus half at squared. So negative 10 equals 20 sine 50 times t minus 4.9 t squared. And then we just get a quadratic to solve, which you can do on your calculator. And if I solve that, I get t equals 3.68 or t equals negative 0.55. So this is obviously a time of flight that I want for this point here. The negative one, that solution kind of comes about from if you extended this curve and kept it going, then it would give me that point there, because that's also got a displacement of minus 10. It's just because of the way we model it is we're basically modeling this curve as a quadratic equation, which follows s equals ut plus half at squared. And we're finding where does that intersect the line y equals minus 10. So that's where this other solution kind of comes from. Okay, let's check these values ourselves. So there it goes. So the maximum height is 22 meters, which is what we calculated. Time of flight all the way to the end, it's about 3.68, which is what we got. Okay, So when it's not symmetrical, we can't just calculate the time to the top and then double it. It's much better to think about the displacement. And so I tend to just do that always, even if it is symmetrical, to be honest. Okay, for this next question, I want to solve something a bit more tricky, a bit more interesting. So this time we're going to fire our projectile at 20 meters per second at 60 degrees, and it's going to be on a platform, which is 15 meters high. Okay, so our scenario looks like this. We've got a 15-meter platform. We're going to fire it at 20 meters per second at an angle of 60 degrees. What I want to find now is its speed, so not its velocity, but its speed and the direction that it's moving 3 seconds in, and find exactly where it is 3 seconds in. Okay, so let's just draw a diagram to start with. It's just going to be something like this, right? Where its initial speed is 20 and the angle is 60 degrees. So we've got one component which is 20 sine 60, and the horizontal component is 20 cos 60. Okay, and we want to find its speed and direction 3 seconds in, so it could be anywhere along this path at 3 seconds in. We're not really sure yet. Let's look at what's going on vertically first of all then. So vertically, u is 20 sine 60. We want to find its speed, so I'm going to say that v is v. A is minus 9.8 because we're looking vertically, and we know that we're looking 3 seconds in. So v equals u plus at. And if I plug those numbers in, I get 20 sine 60 minus 9.8 times 3. So I get negative 12.1 meters per second. So that implies that it is no longer going up, it is now moving down because it's negative. So it started off with a speed of positive 20 sine 60. So it must be on kind of this downward bit because it's moving downwards at 12.1 meters per second. Horizontally, remember there's no acceleration horizontally. It just stays at a constant speed. So horizontally, its velocity is still 20 cos 60. Okay, or if we write that as a decimal, 10. Okay. So what's happening is we've got a vertical velocity of minus 12.1. So it's moving down with 12.1. And it is moving to the right with the speed 10. So if we were to write its velocity as a vector, we could write it as 10 minus 12.1 meters per second. Might want to write it like that. But that would be as a vector. We just want its speed. So what we want is this bit here. Okay, the magnitude of that. So the speed is just going to be 10 squared plus 12.1 squared, square rooted. And I get that 15.7. Okay, as its speed. We should also work out its direction. So obviously it's on the downwards bit, but we could work out what angle it's moving. So we could find this angle in here. So theta would be inverse tan of opposite over adjacent. So that'd be 12.1 over 10. So inverse tan of 12.1 over 10, 50.4 degrees. Now I would describe that as 50.4 degrees below the horizontal or below I. Okay. So if we actually simulate this, and I'll show you the vectors for it. Like that. Okay. Now t equals 3. Let's just see if we can get some times on here. 2.2. Okay, there's 3 seconds. So it's at that point there. I wonder if I can play it again with that on there. Yeah. Okay, so at 3 seconds in, I missed it slightly there. Let's see if I can get it exactly. So at that point there, you can see that it's got a horizontal velocity of exactly the same as at the start, but now its velocity vertically is downwards because it's on its way down. So overall, its velocity is moving in this direction. Okay, so I could try and draw this on here. Okay, so it's going that direction, and the angle that we calculated was in here, 50.4 degrees below the horizontal. The other thing to find is its exact location at t equals 3. I'll do this in a different colour. So we want to think more about a displacement now rather than the velocity. We should also remember that it started 15 meters up. That's going to be important here. Let's do the vertical position first of all then. So vertically, we want to find S. U is 20 sine 60. A is minus 9.8. And T is 3. So we can use S equals UT plus half AT squared. So it's going to be 20 sine 60 times 3 minus 4.9 times 3 squared. So we've got 7.86 meters. Okay, now that's measured from where it started. So we're assuming that this point here is S equals 0. So it's 7.86 meters above where it started. Okay, so that's that measurement there. If we do the same thing but horizontally, so S is S, U is 20 cos 60 because we're looking horizontally, and A is 0 and T is 3. We can use S equals UT plus half AT squared, but A is 0, so it's quite nice and easy. So you just get 20 cos 60 times 3, which is 30. Okay, so that means that this horizontal distance to the particle, so to there, that is 30 meters. Okay, so we could describe its location or its displacement maybe as a vector or as a coordinate. So it's 30 meters across and then 7.86 above where it started. So I'm going to write here from the start point. You might wish to describe it instead as from down here perhaps, in which case the 30 would still be accurate, but the 7.86 would now be 15 plus 7.86, just depends where you're measuring from. Okay, you should now be able to have a go at exercise 6C. You might want to just pick out a few questions from that, or just do the exam style questions from that one. And then the second lesson will go into a bit more detail about some more algebraic questions and just generally some trickier questions to do with projectiles. But what we've covered so far is the basics of projectiles.